Okay, welcome to this video on solving systems of equations. This is part one, solving using the substitution method and an introduction. First, let's talk about what a system of equations is. It's just a list of two or more equations that are to be considered together representing some situation. In this video series, we're going to talk about systems that have two equations with two unknowns, which we'll just use x and y, although it could be any letters. And then some of these ideas apply for larger systems as well. Okay, the solution to a system of equations are just the coordinate pairs, the x, y values, which occur together, which make all the equations in the system true at the same time. To see what that means, let's take a look at this particular system. We have a system here, two equations, y equals 2x minus 3, y equals negative x plus 3. Two different equations here. Let's take a look at this top equation first, y equals 2x minus 3. If I wanted to, I could make a t-chart that has various values of x plugged in, like say if I plug negative 1 in for x, then if I plug that into the equation, I get 2 times negative 1 minus 3, and I get negative 5 out. And so that forms a coordinate pair, right? For x, x is negative 1, and y is negative 5. And that means that's one of the points where if I plug this particular value in for x and y, the equation's true. And what I've done here is I've plugged in different values for x. And so I've got a bunch of different coordinate points. And on the right-hand side, I've made a graph. So each of these lines, like this blue line, is really a collection of all of the infinite little points where if you plug the x and the y values in, it would make the equation true. That's really what the graph of an equation is. It's a plot of all of the points that if you plug that xy pair in, it would make that equation true. Okay? But since this is a system, we have a second equation, right? And I could make a second t-chart here. Right, and I could plot all the points that make that equation true, which in general would be different points, right? So I have a whole bunch of different points here that all make this equation true, right? Okay, so the solution to a system is any xy pair, any point, any x value and y value together, that if I plug it into all of the equations, they all are true at the same time. And so actually there's only one point, right? There's a bunch of points here that make the blue equation true, and a bunch of points here that make the red equation true, but there's only one point here where x is 2 and y is 1 that make both equations true at the same time. And so we would call that xy pair, that coordinate pair, 2, 1, the solution to the system, because it's the only value of x and y that make both equations true at the same time. And one way to solve for a system of equations is to graph and to look at the point or points of intersection. But it's not a very efficient way, right? It takes a long time to plot these things out, to make t-charts. Even with a calculator, you have to still plug things in and compare and find intersections. So what we're after is a way to solve this without having to graph, okay? So that would be called solving a system of equations algebraically, which means to find the solution using algebra without graphing, okay? So the idea behind this is that we need to somehow combine the two equations we're given into one equation so that that one equation has only one of the variables, either x or y. Because if we have that, then we could solve for that, and then we could plug that into any of the equations to find the other part of the solution. Okay? There's two main methods to do this. One's called the substitution method, and one's the elimination method. We're going to cover substitution method in the rest of this video, and then in part 2 we'll talk about the elimination method. Okay, the substitution method goes like this. Here's that same system, y equals 2x minus 3, and y equals negative x plus 3. Okay, substitution says this. At the intersection point, the y values match, and the x values match for both equations. And that means I can substitute one for the other. Okay, here's how that's going to work. We'll take one of the equations, for example, y equals 2x minus 3, and we'll solve it for one of the variables. Now in this case, this one's already solved for the y variable. That's convenient. So what we're going to do then is we're going to take the second equation, right, and wherever I see a y, I'm going to substitute in what the first equation says y is equal to. Okay, so I'm going to write the second equation over again, but instead of y, I'm going to put 2x minus 3. So I'm essentially substituting 2x minus 3 in for the y in the other equation. Now, let me get rid of that parentheses there because it's not really doing anything. What do I have now? I have an equation that I got from combining the first two equations in such a way that the y's went away. I only have an equation with x's, and that means I can solve for x. So let's see, I would maybe do that by adding an x to both sides here and get 3x minus 3 equals 3, and then I would add add a 3 to both sides and get 3x equals 6, and then I would divide both sides by 3 and get x equals 2. Okay, so x is 2. And that means that at the intersection point, the x value is 2, right? So I've got part of the solution. But a lot of people will think we need to stop there, but we're not done, right? We know at this intersection there's a y value also. Okay, to get that, what we're going to do is now that I know x is equal to 2, I can now substitute that into any of the equations to find the matching y value. I'm going to go ahead and take that first equation, y equals 2x minus 3, and that means I'm going to substitute 2 in for the x now, and then I'll find the matching y. Y equals 2 times 2 minus 3, so y equals 4 minus 3, so y equals 1. And that means that at the intersection, the y is 1, and so 2 comma 1 is the solution, which is the same thing we found when we graphed it. Let me go back here. 2 comma 1 was the intersection point. Right? This is just a way to find that point, the x and the y, without having to actually graph. Okay, so if I could summarize the method, it's solve one equation for one variable. In this case, we solve for y, and then substitute what you get in place of that variable in the other equation, so that you have an equation with just x's or just y's. All right, let's try the same thing here. What can we do? Well, it looks to me like this top equation, it would be fairly easy to solve for this y right here. Let me write that over again. Negative 3x plus y equals negative 3. Now this one is not conveniently already solved, so we're going to have to solve for it, which means I want to isolate the y. So let me do that by adding a 3x to both sides. And then I'll get y equals 3x minus 3. And then what I'm going to do is I'm going to rewrite this equation, but whenever I get to the y, I'm going to substitute in a 3x minus 3. So I'm writing this equation over again, negative 3x plus 2, but when I get to this y, I'm going to substitute in 3x minus 3, and that's equal to negative 3. Okay, so I just rewrote this equation again, but when I got to the y, I plugged in a 3x minus 3. Okay, now we need to solve. In this case, it looks like I better do a distribution step first. So I've got negative 3x plus 6x minus 6 equals negative 3, and then I can combine like terms here and get 3x minus 6 equals negative 3, and then if I add 6 to both sides, I'm going to get 3x equals 3, and if I divide both sides by 3, I'll get x equals 1. And that means that the x part of the solution is a 1. But I still need the y part of the solution, so I can go to any of the equations, and actually the easiest one to use would be this version, which is basically the first equation but already solved for y. So let me go to that version of the equation, and I will now substitute 1 in for x. Okay, so I'll substitute 1 in for x, and I get y equals 3 minus 3, or y equals 0. And so the y is 0. So the intersection point for these two lines would be 1 comma 0. This, by the way, doesn't only have to work with lines. You can do this with any sort of equations. Okay, let's take a look at another example. Maybe try this one on your own. What would you do? Pick an equation, solve it for one, and I'll tell you that you might get a fraction on this one. If you do it, it's not necessarily wrong. Pause it, unpause it when you're ready. Okay, let's take a quick look and see if we can come up with a solution. Doesn't really matter which equation I use or how I go about this, but I'm just going to stick with using the first equation. And let's see, we've been solving for y. Let's solve for x this way, just to be different. Let me write the equation again. This time, I'm going to choose to isolate the x, okay? Just to be different, because it doesn't matter which one you use. Let's see, I'd have negative 2x equals negative 3y. And if I wanted to isolate the x, I would divide both sides by negative 2. And negative 2 divided by negative 2 is 1, and 1 times x is just x. And so a negative divided by negative is a positive 3/2 y. Okay, so it looks like my x is 3/2 y. And that means now I can take the second equation, but when I get to the x, now I'm going to substitute in a 3/2 y. So let me write the second equation over again. Negative 3, but now that I'm at that x, I'm going to substitute in the 3/2 y plus 2y equals negative 5. So now I've got an equation with only y, so I should be able to solve for the y. All right, let me put this 3 over 1. Do a little bit of fraction arithmetic here. If I put this over 1, what do I have? I've got negative. I've got 3 times 3 is 9 on the top, and 1 times 2 is 2 on the don't don't let the fractions bother you, right? The way to get rid of fractions is by multiplying both sides of the equation by a number, right? If I multiply both sides of the equation by 2, that's legal to do, right? But if I have half of 9 and I double it, I just get 9, and it's negative. So this is negative 9y. But remember, you have to double everything on the left side if you do that, so that would be 4y equals negative 10. You have to double the entire equation, including the right. But that gets rid of the fractions. Okay, I can combine like terms here and get negative 5y equals negative 10. And if I divide, I get y equals 2. So y is positive 2. That's the y. Now I'm going to need the matching x. So again, I'm going to go back to one of the equations, and a really convenient one to use is the one that you already have solved for the x. X is 3/2 y. And so now that I know y is 2, I'll just put that in here. To do the fraction arithmetic out, we'll put the 2 over 1, and that's 6 over 2, so that means x equals 3. So it looks like the intersection point here, or the solution, is x is 3, y is 2, 3 comma 2. Okay, just a substitution method summary here. To solve by substitution, solve one of the equations for one of the variables, and then rewrite the other equation, and when you get to that expression you solved for in the first equation, just substitute the expression in for that, everywhere that variable appears. Then solve that combined equation for whichever variable you have. Then substitute that result into any of the equations to get the matching other variable. So you can solve for x first, or you can solve for y first. Okay, move on to part 2, and we'll talk about the elimination method.